Welcome to the deep dive. Today we're taking you on a journey that I think fundamentally redefines the city. We're going to be climbing into the futuristic living skyscrapers of 2053 to understand how architecture is merging, quite literally, with biology.
That's right. We're doing a deep dive into bionic design and the whole intellectual movement that's driving it, which is called the third culture.
Yeah.
You sent over a really remarkable stack of sources detailing this shift, and it shows how designers are looking to nature not just for, how things look, but for the actual operational code.
And the vision of the future that's painted it's astonishing. I mean, imagine walking through a city, say, 30 years from now. The skyline isn't just steel and glass boxes.
Not at all.
It's dominated by these organic skyscrapers. We're talking dramatically curved glass facades, flowing white supports that look almost like they were sculpted by the sea, very reminiscent of Gaudi, but alive,
Yeah.
dynamic.
And that's the key, right? These structures aren't just static monuments. They're designed using processes the sources actually call genetic design, and they refine these specific architectural phenotypes.
Okay, let's unpack those terms for a second because they're really important. When we say genetic design and architectural phenotypes, what are we really talking about? Are we saying the architect is programming the rules, the building?
Precisely, yeah. Think of it like this. If a species' DNA is its genotype, the code underneath it all, then the organism that actually grows from that code is the phenotype.
The physical thing.
The physical thing. So in architecture, genetic design means the architect codes the biological principles. That's the genotype. And then a computer algorithm generates the complex optimized form, the phenotype. The building isn't just imitating nature, it's following nature's own evolutionary rulebook for efficiency.
So our mission today is to unpack the whole intellectual journey that gets us from, concrete boxes to these living adaptive systems. We need to see how we move beyond just superficial imitation, what people often call biomimetics, to adopting nature's core principles, true bionics.
And it all hinges on this convergence of the natural sciences, the humanities, and art into what's being called this cohesive third culture.
Right.
But to really get the scale of this shift, we have to go back. We have to look at the powerful, centuries-old scientific worldview that, all our architecture and engineering was built on.
Okay, so let's get into it. We're talking about the rise of scientific rationalism, Enlightenment thinking, dominated by figures like René Descartes and Isaac Newton.
Exactly. Descartes laid the groundwork with his 4 precepts for scientific reasoning.
Huh?
Only accept what is clearly evidenced, break down problems, build up solutions, and check every single step.
And then Newton comes along?
And Newton's work just cements it. He defines these universal laws for mechanics, both on Earth and in the heavens, and that establishes this deterministic, mechanistic worldview.
The famous analogy, right? The universe as a predictable clockwork mechanism.
Absolutely. If you know the starting conditions, you know exactly how it's all going to end. And for centuries, we designed everything based on that belief. Everything is linear, measurable, predictable.
But here's where it gets, for me, really interesting. That certainty was just completely dismantled in the 20th century. So how does a revolution in physics change how a city planner thinks about a block of concrete?
Well, because the giants of 20th century physics just took a hammer to that clockwork mechanism. You had Albert Einstein's relativity showing that space and time weren't absolute.
They were relative.
They were relative to whoever was looking. But the real philosophical earthquake came when we looked inside the atom. Quantum physics.
And we hit the uncertainty principle.
Werner Heisenberg's uncertainty principle. It revealed this subatomic world that's governed by probability, not by strict determinism. You can't know a particle's exact position and its momentum at the same time.
So the universe wasn't this neat, controllable machine anymore?
Not at all. It was complex, random, emergent. Causality itself had to be reevaluated.
And that intellectual crisis, that failure of segmented science to explain reality, that's what paved the way for C.P. Snow's concept.
It had to. If the traditional silos of knowledge were broken, you needed a new approach that could stitch everything back together to solve these really complex problems.
And that's the third culture?
That is the third culture. Snow argued that Western society was dangerously split into 2 cultures. The sciences on one side, and the humanities and arts on the other. The third culture is that intellectual space that integrates them. You need the scientist, the poet, and the engineer all in the same room.
Okay, so if the third culture is the philosophical framework, let's define the language of the design itself. We hear bionics and biomimetics thrown around a lot. Are they interchangeable?
They're often used that way,
Right.
but the sources make a really critical distinction. Bionics, a term coined back in 1958 by Major Jack E. Steele, is the science of systems that are copied from, or, have the characteristics of, living systems. It's
Yep.
about the function, the behavior.
The mechanism underneath.
The underlying mechanism, yes. And biomimetics. That term was popularized by Janine Benyus in the 90s, and it focuses more on the abstraction of good design from nature. It's about the practical application.
So give me an example.
Okay, think of it this way. Biomimetics might focus on how a leaf harvests light. Bionics, on the other hand, focuses on the entire system of growth and energy transfer that makes that leaf necessary in the first place. Bionics is mastering the strategy, not just mimicking the end product.
That's a huge shift from a static form to a dynamic behavior. So if we're now looking at a building as an evolving organism, what are the, say, 3 core theoretical pillars that guide this new design philosophy?
There's sort of the new rule book. First, you have autopoiesis. It's a term from biologists Maturana and Varela.
Autopoiesis.
It describes living systems as networks that are constantly self-producing and maintaining themselves.
Okay, but how does that apply to a building? Does that mean the 2053 skyscraper handles its own maintenance calls?
Essentially, yes. It means the building isn't finished when construction ends. It's a system in constant evolution, designed with the capacity for self-repair, for metabolic efficiency.
The second pillar is complexity theory. This focuses on those nonlinear dynamic systems we were just talking about.
Right, and if we stop looking for simple inputs that lead to simple outputs, it means we have to embrace emergence. Complexity theory says the whole is greater and often unpredictable than the sum of its parts.
So the architect has to give up a bit of that deterministic control.
You give up control, but you gain an adaptive, resilient structure. And that leads to the third pillar, complex adaptive systems, or CAS. This views design as being like biological evolution.
Adaptation, self-organization.
Exactly. The city itself becomes a living system,
Yeah.
constantly optimizing itself in response to its environment.
That conceptual framework is fascinating, but let's get into some concrete examples. What are some of the most surprising analogies we see with bionics in action?
Well, you have to start with the Kingfisher and the Japanese bullet train. It's just a perfect example of looking at principles over form.
I love this story. It's incredible.
The problem with the Shinkansen 500 train was noise. When it came out of a tunnel, the pressure change created this huge sonic boom.
And it was inefficient.
Very.
Yeah.
They realized the air at that high velocity acts like a dense fluid. So the design problem wasn't aerodynamics, it was hydrodynamics.
Which is where the Kingfisher comes in. That bird has a beak that's perfectly optimized for a rapid, clean entry into water with almost no splash.
So the engineers mimicked the geometry of that beak. They applied the Kingfisher's hydrodynamic principle to the train's front end.
And it worked.
It worked brilliantly. The redesign made the train faster, way quieter, and about 15% more energy efficient. That's bionics, understanding and deploying the strategy.
We also see this in structural efficiency, right? I'm thinking of Frey Otto's tensile structures for the 1972 Munich Olympics.
A classic example. He was using nature's forms, spiderwebs, cellular nets, to achieve these incredibly lightweight, material-efficient buildings.
And going back to Gaudí, you see the same thing. The Sagrada Familia's internal columns were designed to emulate trees, managing load through branching fractal systems.
Nature already figured out the best way to hold up weight millions of years ago.
And what's really amazing is the convergence. The sources point out the Musgum mud huts in Cameroon.
Right, which evolved over millennia.
Through cultural necessity. And then you have the engineered towers of Gaudí's cathedral. And they both arrived at almost the exact same form.
The catenary curve.
The catenary curve. Because it's the most physically efficient shape to distribute compressive forces.
It just proves that nature's physics are universal. Whether you apply them intuitively over generations or calculate them with genius-level engineering.
But some of the biggest innovations are coming from processes we can't even see with the naked eye. Tell us about the gecko's foot.
Yeah, this is where it gets really refined. For a long time, no one knew how geckos stick to surfaces. It's not glue, it's not suction, it's pure intermolecular attraction van der Waals forces.
An idea that seemed pretty eccentric at first.
It did, until high-powered electron microscopy revealed this incredible fractal structure of tiny hairs on the gecko's foot pads.
The setae and spatulae.
Exactly, and once that mechanism was understood, the technological leap was huge. It led to the development of biomimetic adhesives.
And these things are remarkable.
They really are. They can stick to almost any surface. They detach without losing their grip. They leave zero residue. The potential for that in construction or even medicine is just massive.
Okay, let's zoom back out. How do we get from observing a gecko's foot to actually coding the logic of a beehive into architecture? This is where the digital frontier of the third culture really starts building those 2053 cities.
It comes back to that core realization. Complexity emerges from simple rules. Biologically, you see these incredibly complex patterns, like the pigment on a seashell, and they're created by a tiny, simple, repeating instruction set.
And we can model that digitally, right, with things like cellular automata.
Yes. Stephen Wolfram's Rule 30 is a great example. It's a very simple mathematical instruction, but you iterate it over and over, and it generates these extraordinarily complex patterns that look just like things in nature.
Like the Konos textile seashell.
Just like it. It
Yeah.
proves you don't need complex input to get complexity. You just need an elegant, simple rule that repeats.
So we can code the architectural genotype, the set of simple rules,
Yeah.
and then let the complex, optimized architectural forms, the phenotype, emerge from the computer.
That is the generative design process, exactly. These algorithms let architects explore the relationship between the code and the final form. The study for the Ground Zero New York Tower is a good conceptual example. They didn't draw that structure, they grew it with algorithms.
And what did that computational growth produce?
A highly complex adaptive structure. It had a porous central column and a crossed helicoidal exoskeleton. The final form maximized structural efficiency, light, wind resistance, all because it was optimized by biological logic, not just human intuition.
And this thinking scales all the way up to urban planning, treating the whole city as a complex adaptive system.
Absolutely. So instead of planning streets on a grid, you model growth using patterns from nature. Planners are using Voronoi patterns, the patterns you see in beehives or cellular distribution, to optimize how a city grows, how it distributes resources and services.
So let's bring this all back to the so what. Why does this matter for you, the listener, right now? This isn't just about creating cooler looking buildings.
Not at all. It's about a new goal: regenerative design. The sources talk a lot about regenerative construction, a concept from Bill Reed, and it goes beyond just sustainability.
Sustainability just means minimizing the negative impact.
Right. Regeneration means creating systems that actively improve the environment. They mirror nature's cyclical, waste-free processes.
And the practical applications from these bionic ideas are directly relevant to global solutions.
Yes, definitely. For example, studying xerophytes plants adapted to arid climates has led to new systems for efficient water collection. Our understanding of photosynthesis is driving huge advances in solar energy tech. It's like Frank Lloyd Wright said, study nature, love nature, stay close to nature, it will never fail you.
So bionics in the third culture really represent this necessary synthesis of science, art, and technology to solve the challenges we're facing in the 21st century.
We've moved from that deterministic linear thinking of Newton to embracing the adaptive, emerging complexity of the biological world. And AI and generative algorithms are now, essential collaborators in creating those adaptive environments we talked about at the beginning.
But this collaboration between the human architect and the computational code, it forces a really major philosophical question, doesn't it? If the code is inspired by nature and the complexity emerges on its own through algorithms, we have to rethink the very nature of authorship, of creativity.
That is the fundamental ethical question this new paradigm raises. When biological code determines the structure and the system is designed for autopoiesis, for self-maintenance and self-production, who or what is the true designer? Is it the human who set the initial rules, the code that grew the form, or the billion years of evolution that created the principle in the first place? That's what this new era of design forces us to confront.